ठीक है ना? इतना टाइम लगा? Good afternoon, friends. So today is the second lecture on polarized neutron reflectometry to be delivered by Dr. Surendra Singh. Before he starts, two things. One, the assignment for small angle neutron scattering by Dr. the questions. So please try to give it as early as possible. My apologies that there's some problem due to which last week it was not uploaded. Secondly, this this module you have 3 days continuous lecture today, tomorrow, and day after, followed by the last lecture on Friday. So please remember you have lecture today, lectures tomorrow. So now I will leave the stage. So now I will sing.
Good afternoon, all. Friday, we talked about little bit in the last phase. We talked about the polarized reflectivity, and I just rushed through about that. So let us start from there only. I mean, what is the polarized reflectivity? Yeah. So I was neutron has a magnet, and if we have a magnetic sample, so in addition to the nuclear potential, we'll have a magnetic potential. Is magnetization, so it has two component, parallel component along to that. So let us assume first this M magnetization is aligned along the direction of H. So in this figure, let us say alpha is 0. So we straight away we have this magnetic interaction, which is this. If it has a applied field, a magnetic non-magnetic layer. So applied field is always there, whether it is applied. So you don't see any contrast due to that applied field, but we have a magnetic sample which has a intrinsic magnetizations. So this will give the this magnetic potential, and the potential is get modified. V is now written Vn plus Vm, and if you see Vm, just now we said it is mu dot B, and if you replace this mu by Gn is gyromagnetic ratio minus 1.913, and mu is neutron magneton, and then this is poly this sigma is the poly spin operator, which it has x component, y component, z component, and this is 2 by 2 matrix, that. So if you put these values here and you just assume it is parallel to this B, then you will have Zn mu double dash m parallel is nothing but the magnetic moment of the magnetic sample. So we have Vn plus Vm, and the plus minus is there because we have neutron has spin up and spin down with respect to the applied field. Only two states it has. Okay, when we have a field, so we will have two kind of potential for spin up and spin down in a magnetic sample. And same way we can get the refractive index, just like for unpolarized we did, where only nuclear part was involved. So we can get n equal to 1 minus lambda square by 2 pi n Vn plus minus Vm, where Bn is the coherent scattering length, that this is nuclear one, and Vm is the. Okay, So you put that value and you will get the Bm as a scattering length, magnetic scattering length. So just see here. Example as well as the Vm, that is magnetic part, which just now we spoke in the previous slide. And then if we have a spin up, then to is given for different element, which is our magnetic element over here. They are a bit comparable. So they give the good, magnetic part contrast. Okay. And as a thumb rule, Friday, I told you, if our magnetization is perpendicular to the plane of the film, like I said, in thin films, mostly we say out of plane magnetizations, like like we have seen all this memory system where we have small bits along the perpendicular direction, which can be used as a memory. So those kind of study we cannot do by polarized reflector. This is one thing, and this is valid for diffraction also. If neutron spin or the magnetization of the sample is along the q direction. Q is defined in this way, like ki minus kf. It is out of the plane for thin films. Then we cannot see anything about the magnetizations in the film because of this law, which we said divergence of V equal to 0 means we don't see any contrast, any variation if we apply magnetic field along the q. It is like a non-magnetic sample only for neutron. Okay, so we can get the information, depth profiling of information in ferromagnetic, because all those other things will be treated as a non-magnetic sample because average magnetic potential on those cases is 0. So this is typically I have shown the briefly I discussed on that day also, but you see here when alpha equal to 0, again same case, when we are talking about the magnetic depth profiling, and here we have a multi-layer of cobalt and copper grown on silicon. Okay, so suppose we have 10 bilayers. So in multi-layers, one more thing is there. And the resultant scattering from that, the interference fringe comes when sine square in your fringes due to their n scatter placed at a same distance. So if you see from that, you will get between two Bragg peak, there should be some oscillations, maximum, minima here in case of multi-layers. So we have this first Bragg peak over here, and 0th Bragg peak is the theta c, and the basic, the oscillation, number of oscillation in between these two will be n minus 2, where n is number of bilayers in your multilayer. Like in our case, there were 10 bilayers, like cobalt, copper, one bilayer, then again another bilayer. There were 10 like this. Between theta c, between angle of critical angle of incidence to first Bragg peak, that this should be n minus 2. So it becomes like, if you count it, 1, 2, 3, 4, these oscillations visual. Sometimes contrast doesn't allow to see these kind of oscillations, but if you see that, and if you you can count them, then you will come to know how many layers you have in your multi-layers. In this case, there are n minus 2 equal to 8, so n equal to 10 bilayers. So from this, we can visually we can see, okay, there is 10 bilayers in this multi-layer. Another things, since a multi-layer, I said we have this magnetizations along the field direction in this case. So we have nuclear as well as magnetic potential. And the R plus is spin up. This red plot over here is coming due to plus sign. Scattering length density, nuclear scattering length density. Here as a depth, this is the surface and this is the substrate, okay, other end. And then you can see different oscillations for nuclear part and magnetic part. I have separated. If you add these two, you red one. If you add this black and green, you will get this blue one. So you can see for R plus, which is showing this red curve over here, the contrast, the density, where that's why you are getting you are noticing in that graphic. Okay, it is something like high intensity Bragg peak is there, but high intensity. Whereas for R minus rho n minus rho m, the contrast is very large. You have nice Bragg intensity as well as the Kizig oscillation for R minus. Okay, so the difference between these two, R plus reflectivity and R minus reflectivity, gives you the detailed depth magnetic moment density in the field, in the multilayer. Like here, we can see the how the magnetizations. If you add these two, rho n plus rho m and rho n minus rho m, then you will get the magnetic part of this is scattering length density, and from that you can get the each interfaces what is the magnetic moment. Okay, so let us see the another case. Where we have now another case where we have magnetizations in the magnetic sample which is not aligned along the applied field. So the applied field will have now m parallel and m perpendicular component. Please remember this m parallel and perpendicular component we are saying in the plane. As I said earlier, out of plane we cannot say anything. We have two components, and as you know, for any spin particle, if you have applied a magnetic field perpendicular to the spin direction or at any angle, the applied magnetic field. So here we have perpendicular component. It won't precede any spin, neutron spin, but we have perpendicular component, m perpendicular, which is perpendicular to the neutron spin. So these spins get preceded, so they can change their spin directions. Okay, so here the case will be different. So let us see, suppose we have a spin up neutron coming, then if we have a spin up after reflection, okay, so this is one possible things if we have both m parallel and perpendicular component. But if there is a precision of spin after interaction, because we have this perpendicular component, so what will happen? Suppose we have spin down, then we will have spin down reflectivity. This R plus plus, R minus minus. Here, no spin flip is occurring because we are getting, sending neutron sample, we are getting a spin up. In this case, we are getting, we are sending a spin down neutron and we are getting a spin. But in addition to these two components, R plus plus. Now we say R plus plus means spin down neutron. These two components called non-spin flip because it is this here no perpendicular magnetization component is involved these two reflectivity. How we derive that I will come to later, but you just understand there are four kind of reflectivity we are getting. Two are non-spin Philip, uh, device, I mean instrument part, but you just understand we can have a R plus minus and we measure the analysis of the reflected neutron. Second spin Philip is coming just because of this perpendicular magnetization. And there is another combination which says when we send spin down neutron in the film and we collect spin up neutron, plus plus R minus minus R plus minus R minus. Can get amplitude of magnetization, which says the structure of a magnetic structure, a layer magnetic structure. Okay, how it is okay. And as I said, this spin Philip is coming due to the M perpendicular component, which is noted over here, sine theta, M sine theta component. Okay. So as we said, we have two perpendicular component. Bx is sine. This is Bx is noted in the previous slide. If you see, I didn't show that xy. Suppose this is x component, this h direction is y component. So the perpendicular direction is the bx, which is nothing but bm sine alpha. If we say bm is the scattering length, magnetic scattering length for the magnetic sample, okay, and by is the cos alpha component, is parallel component. So you can think of putting your these potential kind of nuclear part plus magnetic part, and you can see here this diagonal part which is B plus plus B minus minus, which is responsible for non-spin Philip. Here only the nuclear part is there. And B minus minus. Sorry, we have B plus plus B plus Bn minus. But it is simply like magnetic depth that's minus component is there. But we have two other diagonal, which is B plus minus and B minus plus. In this case, we have only the perpendicular part, Bm sine alpha, this Bx, and we don't have any nuclear part for this. So whenever we have a spin Philip reflectivity from the magnetic sample, it is purely the magnetic component. And putting this potential again in the Schrodinger equations, we will have this kind of coupled equations. Okay, and this one can solve like we did R minus plus. So basically, what we have to split component of the magnetizers, and then we can get the four reflectivity from the sample, and which will give us the detailed magnetic structure. Plus plus and R minus minus, we have this R plus minus and R minus plus component also. Since R plus minus and R minus plus are same in this case, I have just plotted the average of these two. So we have in principle four reflectivity. So non-spin Philip we discussed earlier when the magnetization was totally aligned along the field direction, like this r plus r minus. This, if you say r plus r minus, so in this plus L. So if we calculate, we do polarization analysis after reflection, because we have then only we can collect all these four combination of reflective. Okay, so this will give the detailed magnetic structure. Uh, this is totally the specular part. We discuss X-ray specular reflectivity. We discuss content of the polarized neutron reflectivity, when which one which gives the magnetization depth profile. And if you do this optical specular reflectivity in addition to your specular reflectivity, you film interfaces, okay, like morphology, like depth dependent structure, okay. Though I said in we don't know the uh, will get from the XRD, okay, but layer structure we know, and the parameter which I have already said, which we get from this. So typically I have shown here also this, I showed in the Friday lecture also, which is called spectral reflectivity. And as I said, if you use a position sensitive detector, or a detector which is not a so here you see two figure I'm showing, which is nothing but the interface. It is showing interface like medium 1 and medium here medium, this one is two mediums, here also same medium. But if you see the this morphology, this is in how it's how many times particular height is coming, height distribution we say, height, for both of them will give the same signal. But you can see from specular reflectivity you will get the same interface roughness, but both the interfaces are quite different. I mean, they are not same. As you will see, there are different morphology. So this kind of things happens in the thin films growth, and then the morphology play very important role for their application, as well as then this study becomes very important when there are same roughness but morphology are different. Okay, so these things I will quickly explain, is explained in case of kinetic approximation, where actually this we define d sigma by d sigma. This is differential cross section for any scattering phenomena. And till now we were seeing the ray diagram, like one ray is coming, other that is reflected. But assuming when neutron is falling on the sample, then it generates new source over here, act as a new source, and then generates the reflect phenomena, which might you might have done in the very first lecture, where this basic neutron scattering was there, this kinematic approximation where you use this potential and calculate this sigma by d sigma by d omega. D sigma by d omega is nothing but number of neutrons second into a solid angle d sigma, sorry, d omega. Okay, divide by number of incident neutron per square centimeter per second. So this is different. If you calculate reflectivity, you can calculate from these things like you show the number of neutron incident is suppose phi is your neutron flux incident on your flux is nothing but neutron per centimeter square per second. Okay, and lx ly is your lateral dimension of your sample. Then your sample total neutron incident on sample will be equal to phi lx ly sin theta, and if you calculate over all the solid angles, you get the reflectivity. From this also you get the reflectivity pattern. So same thing we'll use. Now consider interface where we have two z. I mean where we have this kind of interface roughness is there, where the z variation z at one xy, a z at x dash y dash is different. So d sigma by d omega is nothing but this rho square. It is n square b square. If you put the potential value there and then calculate the sigma by d omega, this is very straightforward. You might have done this in first lecture. And by qz, and then becomes eiq dot r minus r dash, where r and r dash is this xyz component at one interface, at one particular point on the lateral dimension in one particular interface point, and r dash is the other point. So if you expand this this one is like zx minus z, because now x dash is there, but we have variation along the z direction because we are dealing about the depth things. So we have zx and z. That they follow the Gaussian roughness, Gaussian variations. If this parameter z minus z dash follow the Gaussian parameters, we can redefine these whole things like gxy, 2 sigma square minus 2. Here this sigma is the actual height variation. Because in specular reflectivity, we don't know the actual height variations. We know both height variation as well as the diffusion component. So if you calculate reflectivity and you have three additional parameters here in reflectivity. In case of specular reflectivity, one is sigma. This is different than specular, as I said. One is xi. This is height functions are correlated in the plane of the film. It says that. An h parameter, this is called Hertz parameter. This h says like if you have h towards 0, then you have like you have zigzag interfaces like here. Here h is towards 0. Here h is towards 1. So h value is called Hertz parameter. It is 0 to 1. Okay. And typically reflectivity, you see, here I have shown this is specular reflectivity. This one is the specular reflectivity, all the way going down. Okay. And then we have collected the off specular at particular angle of incidence. So what we are doing, we situated at this angle of incidence and we got this off specular reflectivity. This is one off specular reflectivity. At another QZ value, another angle of incidence, we have another reflectivity. So we have three off specular reflectivity, one specular reflectivity over here. Okay. And the complete things, if you calculate and if you see how this off specular reflectivity changes by changing these parameters. See other parameter which we have got from specular reflectivity like density, like layer thickness, like roughness. Roughness is again combined thing in the specular reflectivity. But if we preserve those specular as well as off specular reflectivity, we get total picture. This gives us the reflectivity, from source energy. So that this is the relation sigma, different sigma obtained from specular and obscular reflectivity are related. And from this figure, you can see if you change this parameter, your obscular reflectivity pattern changes, and that's why you get the information of interface morphology. Here I have shown two interfaces with different parameters, okay, and like sigma, xi, and h. For this interface, this and then we have plotted this morphology. These values we have obtained from specular neutron reflectivity, and then we have generated these interfaces, two-dimensional interfaces, with for these parameter and for another interfaces. One was the surface. Another one was the buried interface, which shows different morphology parameter, and you can see two interfaces looks very different. Here x parameter is less because it's so more zigzag, and correlation length is higher, whereas in this case we have this h parameter is higher towards 1, so it is like a three-dimensional body. Okay, this one, and this is two-dimensional. Okay, so this two things, if you do specular and off specular reflectivity, we can get please tell me, is there any question, query till now? Now, right, we will see how to measure the reflectivity, okay, and about the instrument, okay. That theoretical part is complete. So we know by now we know we can generate reflectivity patterns from the samples theoretically, and we can, and how to measure that reflectivity experimentally, we will see. Okay, so as I was saying, what is the reflectivity is nothing but incident intensity is there I0 lambda, and reflected intensity is IR. So if you know how much intensity is falling on your sample at angle of incidence theta, and how much and intensity of that neutron is reflected at same angle of refraction, which is equal to both in case of specular, then you can get the reflectivity IR by I. This exactly we measure in our experiment, and as a function of this Q, and that's why this is perpendicular the surface depth of the this is along the depth of the sample. That's why we get the depth profile. Okay, so Q is nothing but 4 pi sine theta by lambda. Theta is angle of incidence and lambda is the wavelength of wave. So in principle, we can do these kind of measurements by two ways. In one case, when we keep constant lambda and vary the angle of incidence, because here this R is function of Q, Q is function of lambda and theta. So we can either vary theta or vary lambda. So that's why there are two cases, two types of measurements can be done. Like in if we change angle of incidence, take a fixed lambda, then reflect will give. And if you change both in Q, this angle of incidence and wavelength Q, then you will get tip. Okay, doesn't matter whether it is variable lambda or variable theta. Okay, so one case when we have a constant lambda, that is called when this is typically happens in the reactor source, where we have a continuous source of neutron, and then we take one particular wavelength, okay, and then change the angle of incidence and do the reflect. And this another one where variable lambda is there. This is typically adopted in the pulse sources like a synchrotron, spallation source based neutron reflectivity. Okay, where we have pulses of neutron of different wavelength falling on the sample. So we have a variation of wavelength at a constant angle of incidence, and we collect the reflectivity. So this is reactor source. This is spallation source. Okay, typically you can though you can chop out the continuous source. Also, you can vary the lambda, and you can do that. But more economic is a constant lambda and variable theta for vector source, which we will explain because this is there in our source, vector source at PRs. So as we said, there are two kind of polarized measurement we can do, polarized neutron reflectivity measurement we can do when we are not analyzing the spin of reflected neutron and we are just doing R plus and R minus. So what should be our instrument in that case? So we should have a neutron source over here. Okay. Then we should have a polarizer. I will explain what is the polarizer. We should have a polarizer because which only one spin comes from the polarizer, then only spin up. Then we should have flipper because we magnetizers. Okay, so we should have a flipper which can change the spin of the neutron. Okay, I will explain the principle of this. Then we will have a sample over here, and then we will have a detector, and we can collect the reflection. And we change the angle of incidence for fixed wavelength. Change the angle of incidence, collect a different angle the reflectivity pattern. A typical reflectivity pattern for spin up neutron, this black one, and spin down neutron is as a function of Q shown. And that this difference between spin up and spin down reflectivity gives you the total magnetization in the sample. This is just from a single film on a substrate. For spin up, for spin down, the reflectivity is like this. So this is the case when alpha was 0. So whole magnetization is along the uh, 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 whole magnet. It doesn't say the structure. And yes, and then we have this reflectometer at BRC, which is followed by here because we have low intensity. And typical, you can see that this is schematic. We have a neutron coming from here, then we have a monochromator here, which we are using silicon monochromator. Then we have a collimator over here, which collimates the beam in the sample. Sorry, in the polarizer, and there is a polarizer. After polarizer, we have just one is pass through simultaneously measure R plus, sorry, specular and off specular reflector. This is the picture of the instrument, and I have which is in the here. Okay, so we have typically instrument for neutron reflectometer is like this, where we don't have an analyzer, and we this is used for getting the magnetization depth profile. Now see. This is the same one. When we don't have a non-polarization, the typical reflectivity pattern is like this. So this I have already explained. So we are getting the magnetization depth profile, not a magnetic structure. Means the cobalt, we will get the magnetization, each of the cobalt layer, 10 bilayers are there, each of cobalt bilayer, but all the magnetization in cobalt layer are aligned along the applied field. I mean, what we say, when we want to know the magnetic structure from the multi-layer or any magnetic thin films, then our instruments should get modified because we, in this case, we have to collect four reflectivity, R plus plus, R minus minus, R plus minus, R minus minus, where we are doing additional thing, which will be clear here. We have a source, again, neutron source, either reactor or spallation source. Then we have to put a polarizer. We need a R spin polarized neutron, so it will give spin up neutron. Then we need a flipper because it will give the spin down neutron also, because we need both the reflectivity. Then sample, and you can apply the magnetic field over here. Okay, and then we should have a flipper also, because in this case after reflection also we need what is the spin of the neutron instrument, flipper as well as analyzer. Analyzer is nothing but Same thing as a polarizer. I'm going to explain these two things later on. And then detector. So we have, after sample, we have these additional things which is required to analyze the spin of the reflected neutron. So in this case, if neutron is making some angle of incidence, this is the magnetic field, then we will get four types of reflectivity. And typical instrument for this is the time of flight method in RAL UK. I have shown here. Here we have a neutron source is over here. Then this is slit one. Then we have a this polarizer, another slit. Then we have a flipper over here. Then guide field is required, because once you have polarized the neutron, your stray field should not flip the spin of the neutron. So it should stay on the same polarizations. So a small guide field, 20 or a slit, is required throughout trajectory of the neutron. So we need a small guide. Then we have a sample over here. Then these are the slits for collimation. Then sample, whole sample environment there. Then we have another flipper, which just now I explained, and then the analyzer over there, and then editor. The typical schematic is also shown down. So we have a polarizer, we have a flipper, we have a this sample, then we have flipper, then this way we can get the cobalt in particular layer has this is magnetic moment, and if we get we get the detailed depth profile of the magnetic structure in our sample. So this is typically, I have already explained this. So typically we have the part of the neutron instrument where a continuous source. Since we have a continuous source, I'm talking about that only here. So we need a monochromator. So monochromator is nothing but these are a single crystal, and using the Bragg reflection, we get a particular wavelength. This I will explain also. So typically silicon, germanium, single crystal are used. Another is the collimator. Collimator is nothing but you have to stop the divergence of neutron, because you have to put that neutron beam on the sample, and which will, so a collimated beam is required, otherwise it will deflect from the sample, I mean from all over, and then you don't have a well defined beam of neutron to do the reflectivity. Okay, so in any experiment we need a collimator, and this is nothing but a neutron absorbing material, and you make a sharp opening on that material, and so that will give you the neutron. I mean neutron passes, the others will absorb from the absorbing surrounding. Okay. Then another is polarizer or analyzer. So we are using super mirror because they give high polarizing efficiency and high intensity. I will explain what is super mirror. Then we need a flipper. There are variety of flippers, but I will explain what is a flipper called pi flipper or DC flipper. Okay, and then sample environment detector. So this is a typical instrument component. Crystal over here like this. Okay, and then different neutron beams of different wavelength are following this, and using this Bragg law, 2d sine theta equal to n lambda, we get a particular wavelength at particular angle of escape. Okay, and that is the simple way of getting this one wavelength from the white beam of the neutron. Okay, we are using silicon 113 in our instrument at Dhruva, and silicon. Why silicon? Silicon has it has very good transmission for the neutron after this instrument will be used by another instrument, so we should not stop other neutrons. Okay, we just need one particular wavelength. We have taken that, and others should pass through this. And also because white or something like that. What we call in our language is second order contamination. So this doesn't do that, because if you see this, comes from the crystal structure of silicon, and crystal structure of silicon is diamond structure, and if you calculate the structure factor for this diamond structure, you will come to know that 2 to 6 won't give any reflex. Okay, collimator is nothing but the two slits, okay, of a different size, neutron absorbing material, and then you get the delta theta from it. And monochromata you get delta lambda, because sometime what happen in your crystal, it is not a perfect crystal, but you have a mosaic spread, because small crystals are randomly oriented, that is for mosaic spread, and that gives you the delta lambda, and this gives you delta theta. Okay, these two factors are very important in neutron reflectivity. I will explain that. So this way, this is monochromata, this is collimator. Another thing is polarizer. So what does the polarizer do? So you have unpolarized neutron. So if you put the polarizer in between, you are separating two spin neutron. Spin up is going here and spin down. So you can separate these two neutron spin. That is called polarized. So there are three ways, mostly, I mean, which are in use. There can be other method, because it is a spin, and you can you can apply other, but practically there are three methods which are mostly used to polarize the neutron. One is called, see, the neutron absorption and scattering depends on the, because it is sections. So if you polarize the helium, one of the spin get absorbed, and that principle is used here to get a polarizing filter. So one of the spin, if you polarize the helium nuclei, one of the spin absorbs and only another spin goes away. So that will give you the polarizing. Another is the polarizing crystal. So there are some crystal which after Bragg reflections gives you the one wavelength, as the monochromator, but in addition to that, they gives also you the only one of the spin neutron. Another spin doesn't reflect. I will explain how, what is the principle of this. Then another is called polarizing mirrors or super mirror. So in this case, we use, so we have this independent, this is the polarized neutron here, you have polarized helium here, both are coming, and after this only one of the spin is transmitting through this. That's why sometimes we call this is the helium filter, helium 3 filter. Okay, so because absorption for spin up neutron is 0, so they will transmit, and another spin down neutron will absorb. This is basic principle for this. Okay, though this is very involved job, how to get itself the polarized nuclei of helium. So there are methods. Square. Okay, sorry, this whole thing is I square. The left side is I square equal to in square plus 2 in im and im square. Okay, so what happens for spin up? There are few materials like a Hustler alloy, copper 2 MnAl, and for not the all plane, one plane which has a d spacing of 3.43 angstrom. Okay, so these planes, and because this magnetic part, because this magnetic structure as well as the nuclear structure has the equal component in equal to im for this material, and for spin up this plus minus come for spin up and spin down. So you can solve from this, you can see from this is very straightforward. For spin up, whole thing is plus, and for spin down this becomes 0. That's why we have, after reflection from this 111 plane of copper to MnAl material, is neutron. Okay, and there are few other material I have listed over here, and particular plane which satisfy this condition and give you the polarized neutron due to the Bragg condition. Yeah. So another is super mirror, which is highly being used. In this case, what happens? This has lower efficiency and there are other difficulties, so it's not so used in practical. This helium-3. This, as you can see, it satisfies the Bragg condition. So if you have a large wavelength, you cannot use it. It is only used for the monochromatic wavelength, because every time you have to change the angle of incidence to satisfy the Bragg conditions to get the polarized. So one wavelength will get at one angle of scattering, another other angle of scattering. So for time of flight or the pulse sources, this cannot be used. So mostly which is being used over all the places in the world is the super mirror polarizer. So as I said, super mirror is a coating mirror, okay, thin films or multi-layer, where one of the spin is reflected, another spin is transmitted. Okay, and basic principle is we have a magnetic and non-magnetic multi-layer. Okay, and for magnetic, we have both the magnetic part and nuclear part. Okay, so you can see if you have a single layer, the reflectivity is like this. When we have perfect multi-layer, we will have a Bragg peak. Okay? So and if you make many multi-layers on this one sample, and depending on the period, because this D1, D2, D3 is nothing but the, suppose you have a multi-layers, three multi-layers in the same structure, and they have different D1, D2, D3, like nickel copper, and D1 is the bilayer thickness, suppose 50 angstrom, 50 angstrom. Another bilayer combination 60 angstrom, 60 angstrom. So as you increase the D1, your Bragg peak shifts towards this. So same thing, same principle is used to get the super mirror. It is nothing but aperiodic multilayers where there are so overlap of many multilayers. So your theta c is also extending, because all this overlap will give you the reflectivity higher, and you will feel the you will feel once you have this kind of things. So single layer has this theta c, but when you make a periodic multilayer where your Bragg is overlapping, so what is basically what you are going to make is you are extending this theta c up to here. Okay, and so theta c has gone up to here. So and since you have a magnetic non-magnetic, so what you are doing, you choose the magnetic non-magnetic component such that for spin up it sees maximum change in refractive index interfaces, because Bn and Bm are comparatively equal. But and it is equal, and B it is it is large difference with the non-magnetic one. But for Bn minus Bm, for spin down, it becomes Bn minus Bm. If you choose such that it becomes equal to the non-magnetic parts of that material, then it doesn't see, the spin down won't see any change in refractive index, so it will transmit. So basically you are doing that. So you will have, suppose this is your reflectivity, you will have spin up reflectivity up to here, and spin down reflectivity will be here on. So you have this region, this is theta, this is reflectivity. You will have this region where you have just spin up neutron, and this theta depends on the wavelength. So typically if you have chosen this super mirror such that your minimum wavelength can give you polarization, then you have higher wavelength will because this theta depends on the wavelength also, and this uh, what we call m. Should I say that? So this super mirror is used for time of flight method also, where we are using different wavelength at some particular angle of incidence. It doesn't depend, because all the wavelength will be reflected from the super mirror. So this is the another way to get the polarized neutron. Now another part was the flipper. Okay, and as I said that if we apply magnetic field at some angle of a spin particle, then that spin presses around that magnetic field. So in this case, same thing. If we applied magnetic field, okay, and this is the equations for this motion. Equation of motion when the magnet. This is the moment of the neutron, and this is the magnetic field, and this is gyromagnetic ratio, and this cross product gives you the this precision, which is called Larmor precision. So this is valid for any spin particle. Okay, and from this, if you calculate, you will get a Larmor precision frequency. Omega L is gamma into B. Is gamma n into B. And if you see what is the velocity, and this, if you this calculate this angular precision of this, then you will get the relation between the neutron velocity. Suppose velocity is v, and what is the distance over which you will have a phi change in your uh, precision. Because what is happening when you apply the magnetic field, this is precessing. Now suppose you applied the magnetic field, this is your spin, you apply magnetic field perpendicular to this, then this spin, which is like this, it will precess around this. Okay, and you have some neutron coming with some velocity, you have applied a magnetic field like this direction and spin up neutron. So, and if this is the d distance over here, so neutron will start precision here, and it will precess like this, and will come out at some angle, which is phi. Suppose the angle is what? Neutron spin was like this, and after this precision in this region where you have applied a uniform magnetic field B, it presses like this, so this angle is phi. Okay, and it is written here. So the distance d and phi is related. By this equation, you can easily prove this. D equal to phi v. V is the velocity of neutron. This is gamma n, and this is b. Okay, Vr. And if this is schematically shown over here. Suppose we have polarized neutron, one spin neutron is coming, and Bz is nothing but this is guided field, which I said this field is required. Otherwise, stray field will be there, and which will try to precess the neutron, and then you will lose the neutron spin. So this guide field is very small. It is around 20 Gauss or something like that. Okay. Then you have a flipper over here, which is nothing a magnetic field you are applying perpendicular to the neutron spin. Perpendicular, it is shown into this plane. Okay. So this is Bf over here, which is perpendicular to the spin of the neutron. You applied uniform Bf along this D. Okay. And then you have to apply it because Bg is already in this direction. So to cancel out that Bg, you have to apply Bc also, because you just want Bf, perpendicular field, no other field for this D direction, uniform field. So that's why it is written here. So total field is Br. Br is nothing but Bz. This is guide field. Bf, which is perpendicular direction field, which is required to flip the needle, and Bc. Bc is opposite to the guide field. Same 20 Gauss you have to apply, because you have to cancel out this Bc. So effectively you have only Bf field. Okay, because this Bg is nothing but Bg minus Bc. Bc is nothing but minus Bg. Okay, so using this equation, you will able to get this. What is the distance required to flip the spin of the neutron? Flip the spin of the neutron means to make this 180 degree. So it is like this. After flip here, you will get spin down, and again you have the guide field, which will keep that spin of the neutron. And if you put the value over here, and you see the use neutron of 1 angstrom, you know the velocity, how to calculate 1 angstrom neutron. You calculate the velocity of neutron, and phi put 180 degree, you will see Br equal to 1 millitesla. You need 1 millitesla applied field for a distance of 1 centimeter only to flip the neutron spin of 1 neutron spin of neutron of wavelength 1 angstrom. So this is typical relation, and you can calculate, and you have to apply. So this is giving you the simple uh, flipper. I mean, how to flip the spin of the neutron. Then sample table. Yes, sample table, because as I said, we have a reflectivity over there, and that is very quickly falls down. So we have reflectivity within 1 degree or 2 degree angle of incidence. So we should have some sample table, robust sample table, which should be able to take all the sample environment things like temperature stays, if you have electric field stays, if you want an in situ growth over there. So all those things arrangement should be available on your sample tables, magnetic field, pressure. So all these things can be done on the sample table. But your sample should be sample table should achieve a rotation of, if you are doing in the uh, uh, theta variation mode. So rotation of the table should be within the few arc seconds. Okay, because in that step we do the reflectivity measure. Okay, and your sample should have all the environment. And you know the neutron detector, how the neutron is detected. Simple nuclear reactions, and one of the element is helium-3 gas detector, where the typical reaction is this. Okay, and as I said, if you use a position sensitive detector, I'm sure you have some idea of the position sensitive detector. It's nothing but a tube detector where helium gas is filled. At the both end, you take the voltage difference, and then you get the positions information. So if you use that, here I have shown here. If you have, this you have sample rough interfaces, thin film sample, and neutron beams falling on that, then you will have all the kind of reflection from there, specular as well as diffuse. And if you use this position sensitive detector over here, you will able to use both specular and obscular reflectivity simultaneously. Okay, so this completes uh, the instrument part of neutron reflection. And X-ray reflection, it is a bit simple because we just have X-ray source, and we need a slit combination, of course, to collimate the X-ray beam also on the sample, then a sample rotation table, and then detect. Okay, so this is the X-ray. But neutron, we need, if we are doing polarized neutron, then we have to have polarizer, then flipper, because we need R plus reflectivity as well as R minus reflectivity, because that difference only will give us the magnetic depth profile. Okay, and maybe just more slides. Uh, yes, I will just explain this, maybe 5 minutes. Practical issue of reflectometry. This is very simple experiment to do, but there are issues, practical issues. In the very first lecture, I have told you this reflectivity pattern falls as 1 by q raised to power 4. If you see after theta c, after critical angle of incidence, this falls 1 by q raised to power 4. So it is falling rapidly. Okay, and you know, for any instrument there is a background issue also. I mean, whether X-ray or neutron. What does that background means? Means the signal noise ratio at particular stage becomes same. So after that, you cannot get any signal from out of that instrument. Here, we can have a stray neutron coming from here and there near to the instrument, that increase the background. Also, the kind of sample you are using, that also contribute the scattering. You might have heard of incoherent scattering, that completely gives you the background. So depending on the samples, so we have this issue, how much Q you can measure this reflectivity. So it comes from the signal to noise ratio for the instrument. So we should have a high flux, high intensity source, okay, as well as very low background over there to get to reach at a higher Q range for any reflectivity. Because the Q maximum for this reflectivity pattern will decide what should be our minimum thickness, 6 angstrom, 7 angstrom on a substrate we can detect from an instrument. And that is gives this relation. T minimum becomes 2 pi by Q maximum. Okay, this is only valid when we have a single film on a substrate, like nickel film on a substrate. If you have a multi-layer, so this doesn't say that. Then you have other layers. So basically this D, as I said, it is coming because of the phase changes. You know, when we put a single layer on the substrate, then that reflected beam, that interference comes because of the path difference from the interface 1 from the interface 2 reflected neutrons. Okay, and that phase difference is giving you this relations d minimum. So when you have a multi-layer, then this is not right. But when you have a single layer deposited on a substrate, then the minimum thickness for that single layer, which we can study from our instrument, the instrument's Q range decide that. Q maximum decides. Okay. So this is the one factor. Another thing comes the footprint effect. Footprint effect is means at low angle of incidence, we have a finite width of the neutron. Okay, but when angle of incidence is low, the projection of that width of the neutron on the sample becomes large. So like this, it becomes delta x by sine theta. Delta x is, suppose in this figure, delta x is our width of the neutron falling on the sample, and this is at the angle of theta. So our projection of this beam on the sample is delta x by sine theta. And if you calculate for maybe 0.1 degree and maybe 0.1 mm, you will see we need a 20 centimeter long sample to cover whole beam. So this is at the low angle, what we call geometrical effect or footprint effect, means the whole neutron is not falling on the sample, so we will not get the whole reflected. Okay, so I will explain when we see. This is another thing. Last slide, I guess. Another thing is resolution of the instrument. Whenever we do experiment, theoretically we can generate the reflectivity pattern. Okay, but in experiment we have inherent things like because each instrument has some resolutions. Okay, and which depends, in this case reflectivity, the resolution factor is defined like this: delta q by q is our resolution, or delta q is our resolution, and the relation you can get from delta q by q whole square equal to delta lambda by lambda square plus delta theta by theta square. Okay, so there are two factors for resolution. One is delta lambda, another is delta. Delta lambda is coming from monochromatic beam. As I said, there is a mosaic spread, so that will contribute delta lambda. Okay, and delta theta is coming from your collimations, because you are cutting down your divergence, and that, but still you have a divergent beam falling on the sample, and that divergence will give you spread in the beam delta theta. So in our case, mostly reflectivity, if you have a monochromator base like graphite, this delta lambda lambda becomes 1 degree. But in our case, silicon, we have this is very small, around 0.1 degree, 1% or something like that, because we don't have a higher mosaic spread silicon crystal. Okay, so depending on the monochromator, you can change this value, but it is basically this resolution for PNR instrument is mostly decided by the beam dimensions. And what happened? What happened? The effect of resolution reflectivity pattern. Here I have shown here three the resolution value I have taken, and I have plotted this reflectivity pattern. So we have very good resolution, 0.02 delta q by q 0.02. Then you can see this black plot. So we see this K-zig oscillation, nice K-zig oscillation coming. Okay, and this oscillation. When we increase this delta q by q, increase the delta q by q means we are making poorer resolution for instrument. Then this these oscillations smear down. Okay, so the features are not so sharp are this in this when you have poor resolution. So this is for resolution effect. So something happens when this maybe single, this will look like when you have a very poor resolution, this will look like a single straight line, and then that can be misguided. So you have to, when you are analyzing your data, you should have this idea of resolution of the instrument. And this is very important because our this also decide what should be the d maximum, a single layer thickness which we can study from our instrument, which is nothing but 2 pi by delta q. Delta q is the resolution of the instrument. So it decides what is the maximum thickness we can study from our instrument. If we make the sample thickness greater than this maximum, then it will look like a single like a substrate. Okay, so I think I will leave it here only, and next lecture we'll see the data analysis and some application. And thank you very much. If you have any question, please you can tell me right now, or maybe you can write. Is there anything? How?
This is different. You don't efficiently apply magnetic field. How easy it is.
Acha, that flipping. Yeah, actually, as I said, yeah, you said, yeah. There is a question, ki how precisely, how is it to precise the neutron spin with a magnetic field? Okay. I was showing this. You can see here. So if you apply a uniform magnetic field, if magnetic field is not uniform, so you have to apply magnetic field perpendicular to the neutron spin. This is spin are perpendicular to this, because then only it will precess by pi degree. Okay. Otherwise, it will make like this here. If it is some angle, it won't give you. It will precess around that. But it should be at 90 degree. B should be the 90 degree to the spin. Okay. So you should have a uniform magnetic field. That is the first criteria. If you have non-uniform, then you cannot precise it. And you can see the magnetic field for 1 centimeter distance, magnetic field is too small, 1 millitesla. So it is not difficult. So it will give you. I mean, this is maximum use in all the neutron reflectivity, and the flipping ratio. Flipping ratio is about 98%, 99%. Can achieve by using just the single magnet. This is the easiest one. There are other flipper also, which I didn't talk about, like RF flipper, where you just resonate that frequency. This frequency, you resonate this frequency by applying RF frequency there in the magnetic field, and then suddenly it make it immediately. It make it 180 degree. But it is easy. This is easy to implement, and it is giving you the flipping ratio of around 99%. So this is not difficult. I think anything else. So I think. So if you have anything, please write me at surendra@brc.gov.in. Thank you.